Ma'am, kindly proceed, please.
Okay, yes, it is live. So, good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly hosted by SAMA, which is South Asian Meteorological Association, and Savitribai Phule Pune University. Today's lecture will be delivered by Professor Anandakumar Karipot, who is visiting faculty here in Savitribai Phule Pune University. And this is the 23rd lecture. Before we proceed for the lecture, I would request Professor Ajit Tyagi sir, who is also President SAMA, to please deliver the welcome address.
Thank you, Rohini, and very good afternoon. It's a real pleasure to acknowledge the contribution of Dr. Anandakumar Karipot Sahib for giving 3 lectures in this series of lectures. The first one was delivered on 22nd February on the natural coordinates, and today we are in the final phase, the 8th module of this lecture series on atmospheric boundary layer and turbulence. And 2 of these lectures are going to be delivered by Professor Anandakumar. So thank you so much. And this is very important part, the turbulence, both convective and mechanical turbulence, which plays very important role, particularly close to the surface than the boundary layer. And many of the aviation accidents do take place because of this turbulence, both in the boundary layer and the clear air turbulence. And its role in atmospheric dynamics is very vital, and therefore we have a right speaker to deliver these 2 talks. And I am sure the participants will immensely benefit from your lectures. And I had been emphasizing the all participants should clear their doubts in question answer session. And even after that, if you have, my request to our esteemed speakers have been that please respond to these, whatever clarification also they seek from you. Thank you so much once again, and wish participants a good lecture from Dr. Karipot. Thank you.
Thank you, sir. Now I request Anand sir to please take over the floor.
Okay, thank you, Tyagi sir, Dr. Rohini, and Sama, for giving me this opportunity to deliver these 2 lectures on atmospheric boundary layer. So this is a subject that I enjoy teaching. I have been teaching this course at SPPU for the last 16, 17 years. So in today's and also the next Saturday's lecture, I will try to give a background or some basic understanding about the atmospheric boundary layer and some of the important aspects, including the atmospheric boundary layer turbulence and all that. So I may not be exactly following that syllabus mentioned, but I will be covering all those topics in these 2 lectures together. So most of the just a minute. So most of the basic aspects I will be covering in today's lecture. So for some background, let's start with the something which everyone knows. A typical vertical structure of the atmosphere. What is shown is the schematic. So it's very clear. The temperature, what is shown is the temperature variation with the height. So in the troposphere, we know the temperature is decreasing with the height, and then there is tropopause, and the stratosphere temperature increases, and again in mesosphere the temperature is decreasing again like that. But we don't see anything marked as a boundary layer here in this sketch, or maybe it is left out or some error. So we can look at some real observations. So we see the what is shown here is the radio sound observations, not the standard radio sound profile where we actually show only the values only at the standard pressure levels, but this is the high resolution radio sound observations from a site in Solapur, close to noon hours observation. So here also we see that more or less it is following that sketch what we saw in the previous slide. So this is a tropical station, so the temperature is decreasing up to the tropopause, which is located close to 17 kilometers above the surface, and then it is increasing in the stratosphere. More or less the following that sketch, and with the radio sound what we can get is maximum up to 30 kilometers. So this profile has up to that much. So again, so you don't see anything clearly as an atmospheric boundary layer. But now if we have access to some remote sensing observations like LiDAR, then we can look at those. So there are two figures in this slide. We see that in the first one, the aerosol concentration shown, but only a few minutes close to the noon hours. So if you look carefully, we see that, okay, what is shown is the concentration. So up to say 800 to 900 meters, we see that pretty large concentration. Then immediately above that, there is a sharp decrease, but then it's kind of a moderate concentration. And then above, say 1.2, 1.3 kilometers, the concentration is reduced drastically. So it gives us some feeling that there is something that is preventing the free mixing, right? Because otherwise, why the concentration, the high concentration stops at say close to 800, 900 meters, and then sharp decrease above that. And again, we can also, so this is only limited to only few minutes, close to early afternoon hours. And we can look the water vapor mixing ratio for a quite long period, so starting from early morning hours, 6 a.m. up to 13 hours. So here also we see that similar features. The large concentration, the water vapor mixing ratio is quite large in the lower part of this troposphere. And immediately above this lower layer, then the concentration is decreasing drastically. But then one thing we also notice is that with the time, as the time progresses, starting from 6 a.m. in the morning, and as we progress, we see that layer with the large concentrations of the mixing ratio, water vapor mixing ratio, the thickness of that layer is also increasing. So these two figures tells us that there is something. The troposphere means it's not just a uniform layer. There is something happening, something special in the very lower part of that the troposphere. Otherwise, why there should be this kind of a behavior in the aerosol as well as water vapor mixing ratio. So now we can go back to that radio sound profile again and try to zoom that lower part, say up to 3000 meters. And then if you look at it, we see that some features, there is, again, this is the air temperature. So decreasing drastically close to the surface. And then close to say 1500 meters, then we see that there is something like an inversion over a small region. Temperature is increasing with height, and then again, it follows the typical tropospheric behavior. So it's like an elevated inversion is there at some height above the surface. This may be something special to Solapur, so we can look at other locations. Radio sound profiles are available. So shown are profiles from Pune as well as Hyderabad and New Delhi. So in all these profiles, we see that here, in addition to the air temperature, I have shown this potential temperature also calculated. And we see more or less the same features. So there is an elevated inversion. Sometimes it is very clear, sometimes it's not that clear. and then there is a sharp decrease in temperature very close to the surface. And then if you look at the potential temperature, so there is a potential temperature also, there is a sharp decrease initially in the very lower part of the troposphere. And then there is a layer with nearly constant potential temperature. And then the potential temperature is increasing with height and then typically follows the tropospheric behavior. So we know that typically the potential temperature increases with the height in the troposphere, but that we are seeing not right from the surface in this case. We see initially a sharp decrease in potential temperature, and then there is a nearly constant potential temperature, and then it starts a sharp increase, and then it follows the typical tropospheric behavior. And here in the case of the profile from this radio sound observation, but shown only at the standard pressure levels. So here you see that the only air temperature is shown here, and air temperature is increasing with height in the lower part. So this is actually from the early morning observations, 5:30 local time. So here the temperature is increasing with height up to 200, 300 meters, and then it is decreasing with the height. So then with this background, now let's try to, so we are kind of clear that there is a layer in the lower part of the troposphere. So we can try to give a definition, basically kind of a textbook definition. So let me read it out. The PBL, the planetary boundary layer, we can define as the lowest 100 to 3000 meters of the troposphere. So it is the lower part of the troposphere formed as a result of turbulent exchange process. So that is very important. So this layer is forming as a result of turbulent exchange process between the surface and the atmosphere, between the Earth's surface and the overlying atmosphere. The layer is forming as a result of turbulent exchange processes. And then some time scale also we have to specify. And this whole layer should be responding to the surface forcing. Whatever happens, whatever changes happen in the forcing at the surface, then this whole layer should be responding to it within a time scale of 1 to 2 hours. So these are all flexible. The height I have mentioned, 100 to 3000 meter, and this 1 to 2 hours, nothing very rigid about that. We'll be talking about it a little bit later. So basically this atmospheric boundary layer, or PBL, so it is a layer of the troposphere that got adapted to the underlying surface as a result of turbulent exchange. And then what are these surface forcing we are talking about, which is basically generating the turbulence. There are a couple of different forcings mechanisms. Basically the surface radiative heating, and during nighttime the heating also influences this boundary layer. So heating or radiative heating or cooling, so there will be differences in the vertical as well as horizontal temperature differences, which generates the buoyant motions, up and down motions, and then generates the convective turbulence. So this particular turbulence generated this way, we call it as a convective turbulence. And then in addition to this convective turbulence, closer to the surface, there is friction, the drag. So as a result of that, there will be wind shear, and that wind shear will be generating, also generating turbulence, and we call it as a mechanically generated or induced turbulence. So these are the two main mechanisms through which the turbulence is generated in this lower part of the troposphere, which helps in mixing and adaptation of this layer to the surface conditions. And in addition to these two, then a minor role is played by the topography and other surface characteristics that also contributes to the generation of turbulence. So these forcings and the turbulence generated as a result plays the major role in the turbulent exchange of momentum, everything. everything between the surface and the overlying atmosphere, momentum, mass, the sensible heat flux, and the water vapor, the pollutants, everything is exchanged between the surface and the overlying atmosphere through these turbulent motions. So we can again represent this this part of the troposphere showing the boundary layer and the region above. So close to the surface, so we have this the atmospheric boundary layer, and then above that the region we call it as a free atmosphere. That is starting from the top of the boundary layer up to the tropopause, we call it as a free atmosphere, and the boundary layer itself during daytime. So that is a convective boundary layer. The turbulence and the exchange mixing is mainly contributed by the thermal convective turbulence, and also the mechanical also contributes. And during nighttime we have the nocturnal boundary layer, and we also call it as the stability. If you look at it, it will be stable in nature, so that is the stable boundary layer during nighttime. So this particular layer of the troposphere is known under different names, and more general terminology is the planetary boundary layer, general for all planets. For us, it is the Earth's boundary layer, and atmospheric boundary layer, or just simply the boundary layer. And so if you look at the characteristics, if you look at the troposphere, and on a time scale of say a few hours, typically at least less than a day, and typical conditions. So this boundary layer, this lower part of this layer that is close to the surface, we can say that keeps the Earth's surface as its private property. So, and then saying that in a different way, the region above, the free atmosphere above, really doesn't know that the Earth's surface is below it, because the boundary layer keeps everything into it, inside, within it, within a few hours. The time scale you are taking is less than a day, a few hours. Then it's like the boundary layer is very selfish, keeps everything in its own custody. So, and the exchange typically is taking place of everything. The energy, the mass, the momentum is taking place between Earth's surface and then the boundary layer. And the scale, what we are talking about, a few hours, is important, because we know that there is no rigid boundary above. So gradually everything will slowly, it will be entering into the region above, which is the free atmosphere. So now, what are the typical spatial and temporal scales? I have mentioned what is the height or depth of this layer we are talking about. Can we say that it's only 10 meter or 100 meter or 1 kilometer or 3 kilometer or 4 kilometer? Everything possible, actually, because the boundary layer undergoes a large diurnal variation. Starts with a very thin layer, and then gradually it can grow. So, and then depending on where we are. So if you take a particular location itself, there it undergoes a large diurnal variation. Starting with a very thin layer, it grows, it can grow up to say 2 kilometer, 3 kilometer, or even more than that, and then decrease during the evening hours and night time. So large diurnal variation, then same location, large seasonal variations are observed. And then there is difference between land and ocean, and then latitudinal or geographical variations depending on the type of terrain, and depending on the prevailing atmospheric conditions and the synoptic influence. So all that matters, and under the influence or under different time and temporal and spatial scales, the depth of the boundary layer can vary, starting from very, very small, for the order of few meters, to a few hundred and couple of kilometers in depth. And the time scale involved, usually we can say starting from few seconds to several hours. So we are saying that the boundary layer depth can vary a lot, So basically it depends on the surface, different types of surface forcing, which is influenced by the radiation, the strength of the winds, the roughness of the surface, the presence and or absence of clouds, amount of moisture in the atmosphere, and the amount of moisture in the soil, and the topography, and so many other reasons as well. Now, to give you some idea about the spatial and seasonal variation of the boundary layer, we are interested over the Indian region. So here I have shown the Indian and the surrounding regions, the Asian regions. So, and with respect to the monsoon, the pre-monsoon, the active monsoon periods, the break monsoon, and the post-monsoon seasons are shown here. So we can see that large variations. So if you take the pre-monsoon itself, the violet color shows the deepest the boundary layer. So the northern north central part of Indian subcontinent, we see that the boundary layer height is this at the maximum of the day, and it is please remember that this is not the actual observations. It is derived from the MERA2 reanalysis data set. So and then averaged over a 1 week period. So we see that during the pre-monsoon April-May period, the deepest boundary layer is seen over the northern and north central part of the Indian subcontinent, growing up to say 3,000 meters. And same season itself, so you see that if you go to the coastal regions, the boundary layer depth is say close to 1,200, 1,300 meters, and the other interior parts of India, so it is say close to less than 2,000 meters, and over the oceans, it's mostly less than a kilometer, 500 to 800 meters in depth. And then during monsoon periods, mostly it is less than 1,500 meters, and over the oceans, again, it is close to 500, 600 meters. And break monsoon, okay, slightly compared to active monsoon, some parts slightly more compared to the active monsoon period, but more or less it remains less than 1,500 meters. The reason is that break monsoon is actually embedded within the season, so the soil and all still wet, so the forcing, surface forcing, convectively generated turbulence will be still weak, so the boundary layer will not grow that much even during a break monsoon period. And post-monsoon periods, it recovers. The boundary layer depth starts growing more, and it is growing more close to 2,000 meters and all that. And we can also look at take different locations and look at the diurnal variations in different seasons to get some idea. So north central part of India, so it is growing more than 3,000 meters in the months of April and May, that is the pre-monsoon season. And then during other periods, during the peak monsoon period, July and August and all that, it is the lowest. It is growing up to maximum up to say 1,000 meters only, and other months with intermediate heights. And peninsular India compared to north central India, the growth is slightly less, but still it is growing close to 2,500 meters. And the coastal regions, as I mentioned previously, so it is growing, say, close to 1,200, 1,300 meters. And over the ocean, so here and all we see that very significant diurnal variation. So, but we don't see that kind of a diurnal variations over both over the Arabian Sea as well as Bay of Bengal. And also there are some variations month to month variations, but not that much compared to that over the land region. The reasons I will be quickly explaining a bit later. So this is what we have explained. Then if you look at the boundary layer over ocean, so we see only very small diurnal variations. No, this is again close the coastal regions, very small diurnal variations. So the soil moisture is usually large, and then the land sea breeze and all influences, and that reduces the boundary layer growth over the coastal regions. And this and the whatever, if you look at the boundary layer depth over the ocean, then we notice that the diurnal variations are very small. The main reason is that the SST, sea surface temperature, doesn't change during the course of a day, mainly because the large heat capacity of the water, and also most of the available energy is used for the evaporation. And then again, the clean water, the solar radiation penetrates to sufficiently large depth, like 100 to 200 meters below the surface, whereas over the land, the radiation is absorbed right at the surface itself. And then the mixing, the ocean currents, and then the vertical mixing within the ocean. So all that contributes to smaller variations in the SST. There can be maybe 1 or 2 degrees Celsius difference during the course of a day, but over the land it can be like the surface temperature, land surface temperature there may be a difference of like 20 to 30 degree Celsius between the minimum and the maximum. So that is one important reason why the boundary layer over the ocean doesn't change drastically. So the changes over the ocean are mostly caused by changes due to the synoptic and some of the mesoscale processes. The depths are usually less than 1 kilometer. But that doesn't mean that if you average out the boundary layer height, and then if you compare the boundary layer height over land and ocean, we may still see that the average boundary layer height over the ocean may exceed that over the land, because over the land it goes through a large diurnal variation. And there can be the boundary layer heights like 10 meter, 20 meter, 200 meter, 300 meter. And whereas that over ocean, throughout the day, it may remain as like 800 meter. And then so depending on the geographical location and all that, it is possible that daily average PBL height may exceed over ocean than that of over the land. And then again, looking at the boundary layer height variations under synoptic influences over the high pressure regions due to subsidence motion. So usually the shallow boundary layer depth we can expect, but don't expect that the boundary layer will become very, very shallow, because high pressure conditions are also associated with clear sky conditions. So there will be a lot of radiation reaching the surface, and then a lot of heating. So there will be two competing effects: the subsidence motion due to high pressure aloft, but at the same time there will be a lot of convectively generated turbulence from the surface. So we may not see a very thin or very shallow boundary layer in presence of high pressure region. Whereas in the case of low pressure region, convergence will be happening at the surface, and we expect that the boundary layer will grow. It's possible, but what may happen is that most of the time when this convergence happens, and if the converging air has moisture, and as it grows, the cooling takes place and clouds may form, and then what is happening within the clouds could be totally different from the actual properties of the boundary layer. So then it becomes a complex boundary layer. So often people take the base of the clouds as the top of the boundary layer. So in that case, under the presence of low pressure systems, the boundary layer may not be very deep as well. So now coming to the properties of the boundary layer. So what is so special about this boundary layer? So the most important or the most special feature of this boundary layer is that it is almost always turbulent. So irregular, random, chaotic motion. So that is something we can say what is turbulence and the size of this turbulent motions. We usually refer it as the turbulent eddies. So it can be, the size of it could be very, very small, of the order of few millimeters, and the largest ones could be having the size of the depth of the boundary layer, like a couple of hundreds of meters. So this, we can see this turbulence in the flow, in the components of the flow, the UV and W components of the flow. And if the flow is disturbed, and under the influence of the flow, the scalars like the temperature and the pollutant concentration, CO2, all of that also will be exhibiting this turbulent nature. There will be random fluctuations in almost all the variables we measure in the boundary layer with the help of some fast response sensors. If you measure, this is how it will be looking like. And then the lower part of this figure, it is shown how the laminar, if the flow is laminar, how it looks like. So molecular diffusion will be dominating, and then diffusion, you can see that it is very, very small in magnitude. But in the presence of turbulent diffusion, so mixing is quite quick. So it is like the calculations have shown that turbulent motion is effective 10⁻⁶ times compared to that of laminar molecular diffusion. So everything, all the exchange between the surface and the atmosphere is taking place through this turbulent exchange, through turbulent motions. So some of the significance of the boundary layer and its the research is mentioned here. So I'll be sharing these slides. You can go through it later. So what are the deciding factors? I briefly mentioned that. We'll go through a little more in detail. So energy transfer to and from the surface. So one important factor is the radiation, both the incoming reflected as well as outgoing radiation, short wave as well as the long wave, and the turbulence generated at the surface due to the convective, due to the differential heating, and also due to the frictional drag. So they are basically responsible for all the mixing. And mechanically generated turbulence will be more if the surface is rougher, the friction is more, the shear is more. So turbulence generated mechanically will be more. So that also will be influencing. And molecular diffusion plays a very small role, and that is confined to a very thin layer of the order of a few millimeters close to the surface. So this process mentioned here has influence on the boundary layer depth and its characteristics. And another important aspect influencing the boundary layer is the entrainment from above. So entrainment, basically it is the incorporation of air from the free atmosphere or the free troposphere into the boundary layer below. And then actually the convective boundary layer, which is present during daytime, is actually growing as a result of this entrainment process. So we can quickly look at the difference between the boundary layer and the rest of the troposphere, which is the free atmosphere. So the properties in terms of turbulence, the boundary layer is almost always turbulence. Its intensity may vary, but it is almost always turbulent. And then the diffusion is through turbulent mixing. Whereas the free atmosphere, usually it is non-turbulent, but turbulence may be present in the clouds as well as associated with the clear air turbulence. And vertical transport of energy, mass, momentum, everything, the boundary layer, it is happening through the turbulent exchange, whereas in the free atmosphere, it is happening through the mean wind. And if you look at the wind speed, the horizontal wind speed, winds are subgeostrophic because we have the frictional effects in the boundary layer. So winds are subgeostrophic, whereas in the and above the boundary layer, it can be nearly geostrophic, and the depth varies. There's large diurnal variation of the boundary layer depth. It can in a range starting from a few meters to several hundred meters, whereas the free atmosphere, the troposphere, the diurnal variations or even seasonal variations are very, very small. Looking at the evolution, so we mentioned that the boundary layer goes through a large diurnal variation. So actually, there is a evolution associated with the boundary layer. So we can explain through a 4-step process. So as shown in this schematic, so if you take starting from the early morning hours, close to the sunrise, a shallow convective boundary layer starts forming. As the sun rises, the radiation comes in, surface is absorbing the radiation, surface start heating, and then the turbulence starts generating as a result of heating as well as due to the mechanical effects. So turbulent mixing starts generated, will start developing, and then gradually it will mix the air. And so as that way, the daytime the convective boundary layer starts forming. But if you look at this figure, you can see that above this convective boundary layer that starts forming during daytime, the previous nighttime stable boundary layer, it is still there. So it will be offering a lot of resistance for this mixing. And this growth is basically taking place by bringing air from above. It can be from free troposphere, or it can be just from the region just above. So initially, early morning hours, the region above is still stable. So bringing air from there is difficult, and the eddies, the turbulent motions that are generated will not be having too much energy, because early morning hours, the radiation, intensity of radiation is weak. So turbulent motions are not very energetic. So growth is gradual in the early morning hours, and then as the day progresses, acute growth, sharp growth in the boundary layer, and then a well-developed boundary layer is forming, or the deep, it reaches the maximum depth close to the noon hours. So this process I want to explain how the boundary layer, daytime boundary layer, is actually growing. So there is a process called the entrainment process. So as the surface starts getting heated, the turbulent motion, convectively generated turbulent eddy starts forming. It's like an air bubble. Over a particular region, the surface is getting heated, the air in contact with that will be heated, it expands and becomes buoyant, and as it is rising, and some of them may be having sufficient energy, so it goes through that layer and reaches that region above, where we have that's a stable region, and if it is the rising air parcel or this turbulent motion is having sufficient energy, it may succeed in going through that stable region above, that elevated stable region. But when it penetrates into that region above, it would have lost its energy, and that stable region doesn't have much turbulence. So it may not get that turbulent motion may not get mixed there, but it will be losing its energy, and then it will be sinking back. So then it comes back to this convective boundary layer below. But in that process, this stable region, this layer may get ruptured, and some air from above, from the free atmosphere, or it may be from the stable boundary layer above if it is early morning hours. So some air from this region above also will manage to come down to the layer below. So let me go back to the previous slide. So the air from here or from here or from here has to be brought down to the region below. And that process is called the entrainment process. And through that, more and more air comes in. And then that's how this daytime mixed layer is growing. So, and then it may remain with a nearly constant height until early afternoon or slightly into the late in the afternoon. And during evening hours, close to sunset or slightly before sunset, the energy reaching the surface decreases. So there may be a loss of energy. Then the energy is reaching to the surface. So surface starts cooling. So surface will become cooler than the air above. And then a stable boundary layer gradually forms. So it is stable nature. And then there is surface is cool. So thermally generated turbulence will not be there. But then gradually you see that the stable boundary layer is also growing. So that growth is taking place, or it may take place if the mechanically generated turbulence, because the shear generated turbulence could still be there even during night time, but it will be weak. The intensity of the turbulence could be weak, but that mechanically generated turbulence will help in mixing, and gradually the stable boundary layer will grow, but it will not grow that deep as during the daytime, because whatever turbulence which helps in mixing and formation of this layer is only due to the mechanically generated turbulence. So that's how during nighttime a stable boundary layer forms. During daytime we have this convectively generated boundary layer. And now if you look at the nighttime period, so during daytime we have that entrainment taking place. So that stable region, that elevated inversion region, we call it as an entrainment zone. But during night time, so we have the stable boundary layer at the surface, and it is cut off from the rest of the region, rest of the troposphere. This doesn't allow anything to mix between the surface and the region above. But this elevated inversion, during daytime it was entrainment was taking place, but there is no thermals going up, and there is no entrainment taking place at night. So we cannot call it as an entrainment zone, but still it is inversion. The temperature will be increasing with height in this region. So we call it as a capping inversion. It still remains as a cap. It doesn't allow free mixing. So the region between this capping inversion and the stable boundary layer below, we call it as a residual layer. Residue, it is residue of the previous daytime's convective boundary layer, because from surface it is cut off, and from the free atmosphere it is cut off. So whatever the concentrations of pollutants, all that will remain, or the water vapor mixing ratio, it will remain more or less the same as in the previous daytime boundary layer, because nothing will be entering from below, nothing will be entering from above. So that's how it is called as the residual layer. So you can go through the slides later when you get it later. So now coming to the vertical structure of the atmospheric boundary layer. So if you take the troposphere, lower part is the boundary layer, and then above that we have the free atmosphere. Doesn't mean that the properties, the characteristics of this atmospheric boundary layer is uniform throughout its depths. So we can vertically, we can look at what is the structure. So this again, basically we can divide this into a surface layer and an outer layer, or inner layer and outer layer. So inner layer, also known as the surface layer, basically it extends from surface up to 10% of the total depth of the boundary layer. That means if the boundary layer, total boundary layer depth is 1000 meters, the surface layer will be close to 100 meters. And within that surface layer, there are sub layers again, depending on the type of surface. There is a very thin layer of the order of few millimeters in thickness, called the micro layer or interfacial layer, where the molecular diffusion is dominant. The turbulence is very, very weak there within that very thin layer, and the conduction or molecular diffusion dominates. And then depending on the type of surface, some surface will be having more roughness elements like buildings or the trees, the forest, which will be offering roughness, and it will be influencing the properties of the surface layer in that canopy, within that canopy, and that layer is called the roughness sublayer. So all that embedded within this surface layer up to 10% of the total boundary layer. Above that, we have this outer layer, and outer layer can, to sometimes we can also call it as an Ekman layer, but convective boundary layer, we cannot call it as Ekman. It is basically neutral conditions, we can say it is an Ekman layer. So inner layer and outer layer, basically we can, the vertical structure will consist of these two layers, and but there are sub layers within the surface layer as well. So these features are again discussed in these slides. So some of the very important properties of this the surface layer, I will quickly go through it. So So in the surface layer, the friction, anyway, it's very will be predominant depending on the surface. Again, so Coriolis force will be very small. So that way. And one very important factor is that the gradients of almost all parameters, all quantities like temperature, moisture, the pollutant concentration, everything will be, and the wind, the gradients will be very, very large in this, the lowest part of this boundary layer. And another very important factor is that the substrate could be very large in the surface layer. So it can be even super adiabatic. In the very lower part of the boundary layer, the substrate could be, the environmental substrate could be more than the dry adiabatic substrate. That means it can be even more than 10 degrees Celsius per kilometer. So rest of the, in typical conditions in the troposphere, we expect a substrate of close to 7 degrees Celsius per kilometer. But in this very lower part, in the surface layer part of the boundary layer, it can be even more than 10 degrees Celsius. So we call it as a super adiabatic substrate. Possible doesn't mean that every day or every daytime conditions it is present, but it may be possible. And if you look at the fluxes of moisture, momentum, heat, everything, with the height in the surface layer, it will be nearly constant. So within the surface layer, irrespective of where you measure, at 10 meter or 50 meter or 60 meter or 100 meter, you may see nearly the same values of the heat flux or the moisture flux. So that is another important property of this surface layer. And there can be organized motion. And above the surface layer, we have the Ekman layer or the outer layer. And the boundary layer is capped by the entrainment zone during daytime conditions, but it allows the entrainment, whereas during nighttime conditions, it is just a elevated inversion. It doesn't allow any mixing with the rest of the troposphere. Now the convective boundary layer, so typically it can have a structure like this. This curve is showing the behavior of the potential temperature, how it changes with the height, schematic. The surface layer, the potential temperature decreases with the height. That is because of that super adiabatic substrate that may be present in the surface layer. And in the mixed layer, because of that well-mixed conditions, the environmental substrate could be matching the dry adiabatic substrate. So we see a nearly constant profile of potential temperature. And then we have this elevated inversion in the entrainment zone. Though I have marked it like this, the depths of these different layers are not fixed. Surface layer almost always follows that nearly 10%. But if you look at the numbers I have mentioned here, mixed layer can vary a lot. This is all with respect to the total depth of the boundary layer. So mixed layer can be 35 to 80% of the boundary layer. Entrainment zone can not necessarily thin as shown here. It can also vary between 10 to 60% of the total boundary layer height. And this, as I mentioned previously, also entrainment zone is, in general, it is a stable zone. Doesn't mean that always it is highly stable. Can be weakly stable, or it can be nearly neutral also. And many of the mixed layer properties I have mentioned here. So a dominant mechanism of turbulence is convectively generated turbulence, but with the sufficient wind, mechanically generated turbulence also contributes to the turbulence in the convective boundary layer and the mixed layer. So very large turbulent motions are possible with the dimensions matching that of the maximum dimensions can match the depth of the boundary layer, like several meters in dimension. These turbulent motions can be, and the mean vertical velocity in general, we say that it is very small, close to the surface, but in these organized motions, highly convective conditions, the mean vertical velocity can reach like values up to say 500 meters per second also. And within the mixed layer, wind speeds may appear nearly constant with the height, but it will remain because the constancy in height of the wind speed profile is because of that well-mixed conditions. The effect of friction is nearly felt throughout the depth of the mixed layer because of that intense mixing, and it will be remaining. That frictional effect is distributed, so it will remain a sub-geostrophic in the mixed layer, and constant potential temperature profile. Gradients of potential temperature will be small, and due to intense turbulence, the time scale associated with the mixed layer will be of the order of few minutes only, because intense mixing, so everything will get mixed quickly, so it will be of the order of 15 to 20 minutes. So this is a special feature associated with the organized turbulent motions, the thermals. So thermals, most of the time it may huge in size, it may form at the surface. As it goes, it may merge and becomes large and then rise through the boundary layer. But under some special situations, sufficiently large horizontal wind and the heat flux, surface heat flux also following certain criteria, then it is possible that huge thermal rising through the boundary layer may get splitted up and form this kind of rotating motions, horizontal rising motions, and then getting splitted, and then sinking motions to both sides. So this type of horizontal roll vortices under the influence of horizontal wind and the rising thermal, and as a result of that, and if these rising thermals are having sufficient moisture, under the influence of this splitting behavior, wherever there is rising motions, clouds may form at the top as the air is rising, and where the air is sinking, there will not be any clouds. So such features are sometimes observed in the atmosphere. So you can call it as the cloud streets. So wherever rising, corresponding to the rising branch of this roll vortice, the clouds will be forming, and then where the air is sinking, then there will not be any clouds. So this type of, so sometimes if you see this type of patterns somewhat similar to this, then that's that tells you that there are thermals and horizontal roll vortices forming in the boundary layer. The entrainment features, I already mentioned that. And now going through the, so during daytime we have the convective boundary layer, and during nighttime we have the stable boundary layer, surface cools. And then that means initially the surface is losing the energy in the form of mainly the radiative cooling, long wave radiative cooling. So surface will be cooler than the overlying air, and whatever turbulence is there due to the wind shear, mechanically generated turbulence, so that will gradually mix that cooled air close to the surface, and that way the stable boundary layer grows, and it may reach a height of couple of 100 meters. Like it may remain very shallow also, like 30-40 meters only, or it may grow to 200-300 meters. Nothing like 3 kilometer or 4 kilometer as we may observe during daytime. And so usually it forms during nighttime, but not necessarily only during nighttime. In higher latitude, especially advection of warm air, surface may be cooler, and warm air advection may also help formation of stable boundary layer. And the most important property is the surface inversion. So in the case of daytime, we have only the elevated inversion at the top of the mixed layer, whereas here we have the inversion at the surface itself. And turbulence, if present, it will be due to the wind shear, mechanically generated turbulence. And turbulence in general will be weak. I should mention two opposing effects here. So turbulence, there are two effects. One is mechanical and the other one is thermal. During daytime, both contributes to the turbulence production, whereas during nighttime, the wind shear generates turbulence, whereas the thermal, it is thermal cooling. Cooling suppresses stable conditions, so that is suppressing. They are competing each other. Wind shear tries to generate turbulence, thermal stability, stable condition tries to, thermal cooling tries to suppress turbulence. So which one dominates? Who is strong? So depending on that, the night can be turbulent, non-turbulent, intermittently turbulence that way. And in general, night times are weakly turbulent, dispersion is reduced. So pollutants emitted into the stable boundary layer may not get mixed quickly. And if there is sufficient wind, horizontal wind, it may get transported to far away locations. So this to show one important feature of the stable boundary layer. The turbulent conditions can vary a lot. So 4 cases are shown here. The nighttime situations, evening to the next day morning. So you can see that this one night, the vertical velocity is shown here. So vertical velocities and fluctuations indicates the turbulent intensity also. So this night you can see that the vertical velocity fluctuations are very, very weak. Only the early evening hours you see that some fluctuations, but rest of the night hardly any fluctuation. So turbulence is very, very weak during this particular night. And this is another night. So kind of not exactly uniform, it is decreasing, but it remains moderately turbulent throughout the night. And another night, half the night it is, the first half of the night is moderately turbulent. Second half is like very weak turbulence. And another situation like intermittent turbulence, no turbulence, turbulence again, no turbulence, turbulence, no turbulence. So everything is possible. So all this depends on who dominates. The shear dominates, shear generated turbulence dominates, or thermal, the suppression of thermal cooling dominates. Depending on that, the nights could behave differently. As a result, the mixing in the night may vary drastically. So night times are that way more complex compared to that of the daytime features. So, and associated with these features, so for example, a night like this, so if it is very weak turbulence, then it is possible that the flow may get decoupled from the surface. So usually the flow will have signatures of the underlying surface because there is constant mixing taking place. But if the turbulence is very weak, then there is no mixing between different layers of the boundary layer itself. So different layers like surface to 10 meter and 10 to 20 meter, 20 to 30 meter, these layers are not talking to each other. They are lying close to each other, but not talking to each other. So no mixing. So that is called the decoupling of the flow. It can get decoupled from the surface and different layers may be behaving differently. So no height dependency. So we call it as the Z-less boundary layer that way. And another important feature that may be present in the stable boundary layer is the presence of low-level jets. It doesn't mean that every location, every night, low-level jet can be present. So you sense what is plotted is the wind speed, horizontal wind speed versus the height. You can see that the jet nose, the maximum in the wind speed is in this case is seen somewhere close to 300 meters. So it doesn't mean that all low-level jets, the nose occurs at this height. It can be close to the surface within 100 meters, or it can be slightly above 300, 400 meters also. And the wind speed also not necessarily becoming very large, like 10 to 20 meter. It can be even less, but more or less we can say that it may reach the speeds of 10 to 20 meter per second. But in this case, you can see that it is, some of them are close to 12, 13 meters. And sometimes the speed, the maximum speed may exceed the geostrophic wind of that location. So we call it that super geostrophic wind speeds are possible. Remember that it is possible. Doesn't mean that always it is like that. And another associated feature, if there are features present like this, so there can be more shear close to the nose of the jet. In this region, there can be more shear compared to the surface. So usually during night time, shear is more here, mechanically generated turbulence is more here. As you go up temperature, turbulence intensity will be decreasing. But if jets are present, it is possible that shear is more at an elevated level. And so compared to that, at the surface, it could be less. So that means more turbulence at an elevated level compared to surface. So it's like the ulta situation. More turbulence above compared to surface. So we can say that upside down boundary layer that is possible in presence of low level jet. And so nighttime, I said that it can be very complex, especially if the situations are like intermittent turbulence. So here, so this figure shows that intermittency in turbulence. Red is the vertical velocity fluctuations with turbulence, without turbulence, like that. And this is actually measurement from a forest, above a forest canopy at different heights. At the canopy height, 1.14, assuming canopy is 10 meter, measurements are at 10 meter, 14 meter, 21 meter, CO2 concentrations are shown. So when it is, the turbulence is well developed, you can see that you cannot make out the difference between the concentrations at the three heights because it is well mixed. But where the turbulence is very weak, there is no talking, there is no mixing between the different levels. Though the separation is between, here is only hardly 10 meter between the different levels, you can see very large difference in the concentration. At the lowest level, everything emitted by the forest at night is 460 parts per million, whereas at 10 meter above the forest canopy height, it is only 380 parts per million. So what is emitted by the forest is not even going up to 10 meter above the forest. So because there is no turbulence during that period. So this clearly shows the importance of turbulence in mixing. And if you calculate the carbon dioxide flux, wherever there is mixing, you can see the large values of the flux. That means there is a lot of exchange taking place when there is turbulence. And when there is no turbulence, okay, the values are very, very small. Just to give you some feeling of the complexity of the night as well as the role of the turbulence in mixing. This is just another night, uniformly turbulence. You can see that CO2 concentration is at the three heights. It's all well mixed. You see this night with the turbulence intensity is decreasing with the time. You can see that initially it is well mixed and the night progresses. You can see that 20 meter height above the surface, concentration is only 370 ppm, whereas here it is reaching 500 ppm. So because virtually there is no mixing taking place in the vertical in the absence of turbulence. Okay, coming to the some tools we commonly use in turbulence analysis and estimation of the fluxes and turbulence intensity and all that. So it is Reynolds, excuse me. Reynolds decomposition and averaging. So we know that the turbulent motions are embedded in the large scale motions. So the way the fast variations in any variable, the wind components or the temperature or the mixing ratio, the fast variations are basically the turbulence. But then if you have a sufficiently long record, then you can average out, then that is the mean. So whatever usually we look at is the mean quantity. For example, we look at the air temperature variation during the course of a day, diurnal variation. What basically we are looking at is the mean variations. We average over every 30 minutes or every 1 hour. And then when you plot it, you see a very smooth varying parameter. It doesn't mean that it is in the atmosphere, it is that smooth. So fast variations are there. So so the instantaneous values, if you average, what we get is the mean quantity, and that mean quantity, if you subtract from the instantaneous value, what we get is the deviation, and that deviation is basically the turbulence. Schematically, it is represented here using the U component of the wind. If you have a large, say 30-minute data, you can average, you can get a mean quantity. And then if you, from the instantaneous values, if you calculate the difference, then you get the deviation, perturbation, that is what is the turbulence. So it is there in all the variables, in the three components of the wind, in the UV, W, the temperature, in the mixing ratio. So all the variables in the boundary layer, we can decompose, we can split as a mean part and the fluctuating part. So usually we refer this as this introduced by the scientist Reynolds. He did a lot of research in the boundary layer related to boundary layer turbulence. Is known after him, Reynolds decomposition. It is splitting the variable, instantaneous variable, into a mean part and a fluctuating part called the Reynolds decomposition. There are certain averaging rules. If there are two variables, A and B, any variable, and constant, then certain averaging rules apply as shown here. And then making use of these averaging rules, and then there are special Reynolds averaging rule. So two variables we can split as a mean and fluctuating part, A and B as A bar plus A prime, B as B bar plus B prime. And then if you average this instantaneous variable, so we can on both sides, both the left hand side and right hand side. So we can write A bar plus A prime average, and then A bar bar plus A prime bar. So that is, we are writing as on the left hand side we have A bar, the mean of the variable A, and the right hand side is the mean of variable A plus A prime bar. So the only way that left hand side equals right hand side, if only if the mean of the fluctuations vanishes. That means the A prime bar, A prime is the fluctuation from the mean. So if you average over that period, it should vanish. Then only this relationship is valid. So that means average of the fluctuation should vanish. So that is called the Reynolds averaging, and based on this basic result of average of fluctuations vanish, there are other averaging rules. There are product of the mean of the product of two instantaneous variables. So we can expand and arrive at this relation, A bar B bar, the product of the means plus the product of the fluctuations in the two variables. So the mean of the fluctuations vanish, but the nonlinear product of the fluctuations not necessarily vanish. So that is another important Reynolds averaging rule. And using these fluctuations in any variable, we can calculate the variance of temperature, variance of the wind components, the variance of the pollutant concentrations, and it can give a measure of the turbulence intensity. Larger the variance, that shows in general, it shows the turbulence intensity is large. And we can also calculate the covariance between the two variables. So it will give the mutual associationship, and from that we can get so you see that the covariance between two variables, and if you expand that, and then we will arrive at this result, which says that the product of the average of the product of the fluctuations, so which we are seeing here also. And so we can calculate the variance, we can calculate the covariance, and we can, another important quantity we usually use in boundary layer research is the turbulent kinetic energy. So if we have the fluctuations in the wind components, in the UV, W components, and then half of the square of these components average out of sufficiently large averaging periods, that gives the turbulent kinetic energy. So this also gives a measure of the turbulence intensity, and people look at the budget of TKE to look at how the boundary layer evolves, and to explain various features. And coming to the last topic of today's lecture, the fluxes in the boundary layer. Flux, basically it means the measure of the exchange between the surface and the atmosphere, or between different layers of the atmosphere. So according to the basic definition, the flux of any quantity, let it be heat or moisture or momentum, so it is a quantity transferred per unit area per second. A very basic definition of the flux. So it can be heat flux, water vapor momentum, or CO2 flux. So that quantity, so heat per unit area per second. So based on this definition, then, and the units we know, heat is expressed in joules, and that per unit area, so per meter square per second, joule per second is watts per meter square. Similarly, moisture flux, moisture, okay, we can say that, okay, this much mass of moisture in the air, so much moisture transported across unit area per second. And momentum of flux, momentum is mass into velocity, so kilogram meter per second is the unit of momentum, and that momentum transported across unit area per second. But now we see a difficulty here, because we don't usually measure the heat directly in the atmosphere. We can measure, but usually the sensors we use are not for measuring the heat. And usually we don't separate out the moisture and weigh the moisture to get the mass of moisture. So we don't usually measure the heat or the mass of the moisture in the atmosphere. So according to this actual definition of the flux, it's very difficult to measure or calculate the flux. So we can express the flux in a more practical or convenient way in terms of kinematic flux. So what we can do is that we can normalize the fluxes, the original fluxes, using air density, or in a slightly different normalization we can use, and express the fluxes in terms of the quantities or the variables we usually measure. For example, heat flux. So the actual unit is joule per meter square per second. We divide that with the rho Cp. Rho is the density of air, and Cp is the specific heat capacity at constant pressure. So density kilogram per meter cube, and Cp is joules kilogram per Kelvin. And what we get is Kelvin meter per second. Kelvin is the unit of temperature. So that's the quantity we measure. And this is the wind speed. So that also we usually measure in the atmosphere. So this way, we can express the flux in terms of the quantities we measure. Moisture flux, we can normalize with the density of air and express as the mixing ratio, kilogram moisture divided by kilogram of air. This is actually the mixing ratio multiplied by the wind speed in that particular direction. So we get the moisture flux. So like that, we can get any fluxes in all the three directions, because what we need is the quantity and the flow in a particular direction. It can be in the vertical, it can be in the two horizontal directions. So all this heat flux, moisture flux, we will have three components, in the vertical and also in the two horizontal directions. Whereas the momentum flux, not three, we will have 9 components. You can think about the reason why 9, why not 3. So now fluxes in general, what we discussed is the mean flux, but now the boundary layer, we know that it's the two important aspects. One is that the turbulent motions are very, very important, but then why should we care about the turbulent motions? Why not the mean motions? So when you talk about the exchange between the surface and the atmosphere, or the different layers in the boundary layer, so for the exchange to take place, a particular quantity has to be transported in that particular direction. So there has to be that quantity, and then there has to be a motion in the particular direction. So in the vertical exchange, which we are interested, horizontally advection takes care, but in the vertical, if you look at the mean vertical velocity close to the surface, in most of the situations, we know that the mean vertical velocity is negligible, very, very small. So it cannot transport almost anything in the vertical. Heat or moisture cannot go up, but we know that it is happening. A lot of heat, a lot of moisture, energy, momentum, everything is being exchanged between the surface and different layers of the atmosphere in the vertical. So something else is important. So we cannot rely on the mean motion, but we do know that there is turbulence. So mean vertical velocity is negligible. So then we have to look at how the exchange in the vertical is taking place with the help of turbulent eddies. So the mean vertical velocity is nearly 0. Exchange is taking place, and that is happening through turbulent exchange. So we call it as this eddy flux concept. So to explain that, a typical profile of potential temperature during daytime is shown. So decreasing with the height in the lower part of the boundary layer, or it can be temperature also decreasing with the height. Now think about a situation, and so there are up and down motions in the vertical taking place. Think about a particular instant, an air parcel which was originally at a lower level, so it got adapted to the temperature at the lower level, so it became buoyant and it is going up. So it initiated at a lower level, it is having higher temperature compared to the levels above. And assume that you have some sensor located somewhere here. So as this fellow is crossing that sensor, it is measuring at a high frequency rate, 20 times a second, for example. So momentarily, as this eddy, the turbulent motion is crossing, it will momentarily record a higher temperature. So it will show a higher temperature at that particular instant. Now, at the same time, up and down motions are continuously taking place. Another fellow originated at a level above. So if you look at this temperature profile, higher levels are having cooler temperatures. So this one is having cooler temperature and it is coming down. So, and as it is crossing the sensor located here, so it will record a slightly lower temperature. And this is happening, up and down motions are continuously happening in the boundary layer. And as it is going up, it corresponds to a positive vertical velocity according to sign convention. So fluctuations will be positive. The temperature fluctuation also, theta prime or T prime also will be positive. So according to our definition of flux, product of flow and the quantity, that is the flux. So W prime, theta prime, both are positive. So you will get a positive quantity, positive heat flux. And that time itself, as it is coming down, the sign convention W is negative. So this will be, fluctuation will be negative and temperature will be decreasing because air parcel originated at a higher level. So theta prime will be negative. The product, W prime negative, theta prime negative. So product again will be positive. So during daytime, and if you, so many are taking place like this, instantaneous, like very, very fast. So if you take a 30-minute period and then average all these fluctuations going up and coming down, product of W prime, theta prime, you will be getting mostly positive values. So you'll get a positive heat flux during daytime. So we know that surface is warmer, air above is cooler during daytime. Heat has to be transported from surface to the air above. So you get a positive heat flux. And nighttime, the situation is opposite. Surface is cooled, air above is slightly warmer. So the profile will be having opposite, surface inversion. And then as the air is going up, you will record a negative temperature fluctuations. So W prime positive, theta prime negative. And when air is coming down, the levels above, temperature is higher compared to the surface during night time. So W prime negative, when it is coming down, theta prime will be positive. So the product, and then you average over a 30-minute period, you will end up with a negative heat flux. So in this case, if you average the vertical velocity, you will see that mean vertical velocity is 0. But if you average this product of W prime, theta prime, you will see non-zero meaningful values, positive during daytime, negative during night time. So how we can see that in actual time series is shown here. So this is during daytime, the black is the vertical velocity fluctuation, just a 30-minute segment. You can see that the turbulent, fast variations in vertical velocity as well as temperature. The fluctuations are shown. The mean is removed, only the fluctuation. So you can see that whatever I was discussing, the air going up. So this is the 0 line. So the values of vertical velocity are above the 0. So temperature also above the 0 line, positive. So W prime, theta prime. So when W prime is positive, theta prime is mostly, but you can see that now if you look at very carefully, some cases it is not following because it is turbulence. Turbulence doesn't behave the way we want exactly. It's random, chaotic. So those signatures are also there, but mostly when W prime is positive, theta prime or T prime is also positive. So if you calculate the product, so product is shown here. W prime T prime instantaneous is shown here. You can see that mostly all the energetic fellows are above the zero line, means it is positive, but there are some not following that, some are negative also. But if you average out this over a 30-minute period, then you are seeing W prime T prime average over this period is like 0.178 Kelvin meter per second. Remember that this is in kinematic unit. You can multiply with the rho Cp. So rho is 1.2 and Cp is 1004. So multiply with the roughly 1000. So this is something like 180 watts per meter square. So during a daytime, hot daytime period, so during that 30-minute period, so much of heat is transported away from the surface. So though the mean vertical velocity is zero, the turbulent motions are effectively transporting heat. And this is applicable not just for the heat. The same thing you can apply for the moisture. You can apply for the momentum. Very well, you can apply this concept and get the this. And this is during the night time. You can see that the time series, you can, the intensity of turbulence is weak. Remember that the scale is different here, only varying between -1 and 1 I am showing, but here it is between -3 and +3. So intensity of turbulence during night time is very, very weak. And this is the W prime T prime, the product between the two time series. And you can see that, yeah, large negative values, but intensity is weak. And if you calculate the mean over this 30-minute period, you can see that it is negative 0.0102. And if you convert this to actual units, it is only 10 watts per meter square. So night times, turbulence is weak. And so we don't expect a very large heat flux in the downward direction from air to the surface. There will be transport because air is warmer than the surface in the lower layers. So some heat transport will be there from the air immediately above the surface to the surface, but it will be very weak because turbulence intensity is weak. It will be on the order of 10 watts per meter square or 20 watts per meter square of that magnitude in the negative direction. So I think with this I stop here, and we will continue this in the next class, slightly advanced topics also. So thank you very much. I don't know how much time I took actually, but if there are questions, I will try to answer.
Thank you, sir. Yes.
Thank you.
So before we go to the question, can you unshare your screen, sir?
Okay.
Before we go to the question answer session, we will take a quick photograph. Meanwhile, participants can post their questions in the Q&A box. I request everyone to switch on their cameras.
Stop sharing.
Maybe on the top side it will be, sir. Stop share.
Did it stop? No.
No, no.
No, okay. Yeah, I see it.
Yeah, okay. Yeah, so Ashwin, can you take the picture? Okay.
Thank you.
Now I request Mrunal Naik from IITM to please moderate the question answer session.
Sorry, I took 1.5 hours. I didn't.
No, it was 50 minutes. It's fine, sir.
Yeah. More.
Okay.
It's 4:30 now, right? Yeah.
Yeah. Mrunal,
Thank you, ma'am. Thank you, sir.
Yeah.
So there are a couple of questions. The first question is from Dr. Ira Upadhyay. How can the daily cycles of PM 2.5 concentration be analyzed to see the influence of entrapment zone?
Daily concentrations.
Daily cycles of PM 2.5 concentrations.
Diurnal cycles.
Yeah.
Maybe diurnal cycles. Okay. So influence of entrainment. So entrainment is basically happening during the daytime in the convective boundary layer. So that means the air from above, air from the free atmosphere is entering into the boundary layer, entering into the mixed layer and getting mixed over there. So so the concentrations of PM 2.5 and the rest of the troposphere usually could be different, and when it is coming down into this mixed layer, into the boundary layer and getting mixed over there, so that way it may get diluted. That will again depend on the PM 2.5 the layers above. It is possible that if more PM 2.5 is getting transported from faraway regions due to other influences, and then if that is getting mixed to the atmospheric boundary layer, it is possible that the concentration may increase also. But usually, assuming that the source of PM 2.5 is close to the surface, in that case, and free atmosphere is with less PM 2.5 concentration, and in that case, the PM 2.5 concentration in the lower part of the boundary layer may reduce during the course of the diurnal period, especially during daytime period when this entrainment is taking place. I hope I answered the question.
Yes, sir. So the next question is from Josen. Which are the areas of forecasting these ideas are practically applied?
Areas of forecasting, I'm not sure what forecasting of what actually.
Sir, maybe he means in which areas of forecasting these ideas practically can be applied.
Yeah, that's what I'm also thinking. It could be like air quality
Yeah.
forecasting.
Mhm.
So air quality forecasting, or it can be the weather forecasting in every way, anyway, irrespective of whether it is weather forecasting or air quality forecasting. So this boundary layer is very, very important, because the very basic aspect that all the exchange of almost everything is taking place through the boundary layer. So, for example, the moisture, if it has to enter the air above, it has to take place or through the boundary layer, or the exchange of heat between the surface and the atmosphere, and between different layers. So all the exchange, the momentum, everything has to take place through the boundary layer. So the boundary layer basically decides the exchange, all the processes. So whenever we numerically model this, it is very important that all these processes, the height of the boundary layer, and all these turbulent aspects are properly put into the model. But there are limitations, so we cannot resolve all these turbulent motions in all types of numerical models. Usually, most of the numerical models dealing with the weather forecast, even air quality and all that, generating the flow fields, they don't resolve all these turbulent motion. So these are all parameterized in or means approximated and put into the model. And how good these parameterization schemes behave or recreate, simulate the actual scenario. So accordingly, the weather field, the flow field, or whatever we are simulating also will vary. So it's very important that all these processes are properly parameterized in the numerical models.
Thank you, sir. There is one more question for Krishna Priya. First of all, she is saying thank you for the wonderful lecture. It covered everything about boundary layer, and her question is regarding the oceanic boundary layer. As you mentioned, the oceanic boundary layer can extend up to 800 meter, which is deeper than its land counterpart. Is this greater depth due to low variability in sea surface temperature during the daytime?
Yeah, just during the daytime. SST, if you look at during a diurnal period. So during a diurnal period, the SST variations are very, very small, maybe 2 to 3 degree Celsius only. I mean, a difference between the maximum and that diurnal temperature range can be only 2 to 3 degrees Celsius. But whereas the same thing over land, the land surface temperature during early morning hours, the minimum can be say 20 degrees Celsius, and during real hot conditions and bare soil surface, dry bare soil surface, the SST may reach 55 to 60 degree Celsius. So diurnal temperature range is so huge over land compared to that over ocean. So one very basic reason or the factor that supports the boundary layer growth is the surface heating and the thermally generated turbulence, which is mixing the air, and that's how the boundary layer is forming, right? So so the temperature over the ocean is not changing at all. It's not increasing that much, not changing much. So the boundary layer may remain. If it is say 600 meters, it may remain the same throughout the day and night, throughout the diurnal period. Whereas over land, it may be early morning hours or nighttime periods. It may be 10 meter, 50 meter, 100 meter. Whereas during nighttime, depending on the location, the season, and all that, it may be daytime. It may reach say 1,500 to 1,000 meters like that. But then if you average, it may. It is. I'm not saying that everywhere, all locations, it will happen. It may happen that the average boundary layer ocean, especially over higher latitudes, over land, it may not go to 3 kilometer, 4 kilometer. Whereas over the land or the ocean, it may reach, ocean may be warmer than land also. It is possible during some seasons over higher latitudes. So in that situations, average boundary layer height over ocean may be more than that over land. That's what I'm telling. So SST variation is the key. Less variation in SST. Yeah.
Thank you, sir. There is one more question for Kameshwari. Sir, if this scenario where the high wind speed and mesoscale eddies over ocean, will there be difference in boundary layer structure over mesoscale eddies and surrounding ocean where temperature is relatively warm?
Will you please repeat that? That question is not very clear to me.
Okay. Where there is high wind speed and mesoscale eddies over ocean, will there be any difference in boundary layer structure over mesoscale eddies and surrounding oceans where temperature is relatively warm?
I'm not sure whether she or he is talking about the oceanic boundary layer within the ocean. I'm not sure, because question talks about mesoscale eddies.
Yes.
So anyway, from whatever I understand, okay, the higher the wind speed, it is possible that the shear generated turbulence could be slightly more over the ocean. But then how it can be, what is about this mesoscale eddies mentioned, I'm not very clear. So high wind speed conditions, shear could be naturally more, and that could help in mixing, and slightly deeper boundary layers may form over the oceanic region. So that's what I could say from whatever I understood from that
Sir,
question.
she mentioned oceanic boundary layer and mesoscale eddies in over the ocean, in oceans.
Yeah, but within the ocean.
Yeah, within the ocean, yes.
I'm not very sure about
Yeah.
that aspect. Yeah, definitely there will be influence of this wind shear, and then yeah, the oceanic boundary layer and the eddies also. But how exactly yeah, it behaves, I have not looked into, or I'm not very clear about that.
So there is one more question from Krishna Priya. Like, as you mentioned, winds in atmospheric boundary layer are subgeostrophic. What does subgeostrophic means?
Subgeostrophic means less than the expected or expected geostrophic wind. So when we say geostrophic wind, so that means there is balance between these two forces, the horizontal pressure gradient force and the Coriolis force. So for that balance to reach, there has to be certain wind speed has to be attained. So very low wind speeds, if you calculate the Coriolis force, then it will not be large enough to balance the pressure gradient force. So when you say geostrophic wind speed, so that can attain corresponding to a particular wind speed. So it has to be sufficiently large wind speed, say something like, say, anyway, all that depends on the latitude and all that. So say 15, 20 meter per second. But then in the boundary layer, so we have this effect of the friction actually. So effect of because of that, so there are three forces, not just two forces. So friction will reduce the wind speed. So that way wind speed will remain. So that means the geostrophic balance will not be achieved. The third force is there. So because of that, the wind speed will remain less than that geostrophic wind speed expected for that particular pressure gradient and that location. So that is what is meant by this sub-geostrophic, less than the expected geostrophic wind speed. So that is usually, throughout the boundary layer, that is the case, but in some rare situations, as I mentioned, in the presence of low-level jet, it is possible. Sometimes it is possible. Low-level jet, the speeds may increase to sufficiently large values, and in some situations it may exceed the geostrophic value. So we can say it is super geostrophic, more than the expected geostrophic wind of that location and gradient, pressure gradient.
Thank you, sir. So there are no more questions. Yeah, that's it, sir.
Okay,
Thank you.
Thank you, Mrunal. Before we go to the vote of thanks, I would like to mention the statistics for today. So 90 participants have recorded their attendance, out of which 85 participants have rated it as excellent or very good. So thank you very much, sir.
Thank you.
Just 2-3 announcements for the participants. This was the third last lecture in the weekly online series, which started on 18th January 2025. So 2 more lectures are to be going to be held, and after that there will be the exam. So please do attend the lectures regularly. These 2 lectures especially, we will be giving announcements for regarding the exams, which coming exam, which will be on 26th of July 2025. Okay. So I request Ashwin Jadhav to conduct vote of thanks.
Thank you, madam. I will share this. Slide is visible, right?
Yes.
Yes.
So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 23rd lecture in our weekly online lecture series on atmospheric dynamics and its application to climate sciences. We are especially grateful to Professor Ajit Tyagi, President of SAMA, for his warm welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor Anandakumar, sir, visiting faculty at SPPU, Pune, for delivering an enlightening lecture on definition, turbulent characteristics, convective and mechanical turbulence, Bousisnesq flow. I would like to acknowledge Dr. Rohini Bhavar for moderating the session and Ms. Mrunal Naik for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to all the participants and attendees who joined us from across the globe and the dedicated team members at Savitribai Phule Pune University for their invaluable role in organizing this lecture. Thank you. Thank you so much.
Thank you, Ashwin.
Thank you.
Before I would like to conclude, I would request if Tyagi sir wants to say something.
No, it's really thanks to Dr. Karipot for the insightful and very, very exhaustive lecture, and it really addresses all key issues related to the boundary layer and the turbulence. So thank you so much. And
Thank
as you have told that, yes, we have to now sound all participants to prepare for the final exam. And also we should be doing our homework now for compiling the abstracts and also conveying our thanks and appreciation to all the speakers. So
Yes, sir.
that is our in-house thing. But thank you once again, Dr. Anandakumar Karipot sahab, for
Thank you.
your lecture.
Thank you.
Thank you, sir. So I will stop the